Hey everyone, welcome to this episode of the Sim Step Up series. My name is Brian. Today we're talking about a very important topic if you want to be really proficient with assembly analysis, and that is shelling strategies. Today's case study, we're going to be looking at the top platform in a grain elevator structure, and it's a lot of weldments, it's a lot of sheet metal, there's some fasteners, and the only way I'm going to be able to solve this is to evolve my strategy from solid into shells. But I can't go and just use beams because I need a lot of resolution in my results. I really need to see where the critical stress is and bending in some of these floor supports, as well as where the critical joints are, as well as actually taking some fastening features like welds and fasteners into account. So we're going to set this up from scratch from the SOLIDWORKS solid geometry and get into these results by the end of this episode. The main thing I want to stress today is how important it is to be comfortable in SOLIDWORKS with surface modeling. And I'm not talking industrial design, swoopy shapes, modeling a mouse surface modeling. I'm talking about just the nitty-gritty core features of offset surface and mid-surface. So we're going to spend a lot of time in there talking about 5 different strategies to actually get to a shell element type. And then when we get to simulation, we're going to talk about how shells are defined and some of what the ramifications are for that. And along the way in that, I'm going to uncover my best strategies for working with shells, especially as you evolve to having hundreds of shell bodies. And then finally, I'll spend a few minutes talking about the different results you get when you have shell elements, as well as a few pointers if you're looking for including fastener results or weld analysis. So when we look at shell elements, why do we need them? Well, typically because solid would just be too inefficient. If you look at the sheet metal part on the right, if I want to mesh that with a solid, remember that to get good bending stress with a high quality tetrahedral, I need about 2 elements minimum across the thickness. Okay, so if this is 20 thou sheet metal, that's going to be an extremely small element type. And that's just for this one solid part. What about when I get to assembly size? So things like sheet metal, weldments, they're perfect candidates for shell because the wall thickness is almost perfectly uniform, and it's also much thinner than the overall aspect ratio of the part itself. Now, shell elements, there's also a couple side benefits of using shells, and mainly that is since they're virtual thicknesses, I have the ability to specify thickness as a parameter. So if I'm still in the design phase, I can use the shell thickness to kind of determine what gauge or what wall thickness I need for some of my structural steel elements. I'm also able to account for more fastening methods. And this is one reason why I tend to go shells versus beams as I get closer to a validation study, is because shells still have the shape of the part. I'm not simplifying it into a single linear toothpick-like element with just a ball joint. So shells are all about efficiency and kind of that middle ground between solids and beams. And this diagram kind of illustrates that. Obviously, if we're on the far left, I have this low aspect ratio part. And looking at it, there's really no way that I could model that thing as a surface and still be able to visualize what it is. So sometimes deciding which element type to use is pretty straightforward. Something chunky is obvious. That sheet metal part I just showed you, after this lesson, hopefully you feel, oh, that's pretty obvious, that's a shell. But in the middle, well, it really depends. It can be difficult. This little lid piece there, you could almost visualize that as a shell. And what I mean by that is if you can imagine representing this part, this solid part, as just a surface body in SOLIDWORKS and still have the same visual of the structure, it might be a good candidate. I mean, look at this example here. This is the monitor arm from concept before CAD. And think if we wanted to analyze this. Now, again, I could throw solid elements at this, but look how thin the sheet metal interface bracket is, if you can see that. I would have millions of elements, and I'd be waiting an hour at least for this thing to solve. So what I would do is the red sheet metal, that instantly becomes a shell in my mind. The white sheet metal instantly becomes shell. I also have bolts. Now, bolts we'll see towards the end I can still accommodate with a shell mesh. These black pieces, these support arms, now these, you can't really see them too well, but they're probably solid at first. But if I had a giant assembly where there was 100 of these holding up some kind of structure, I might think about simplifying them to a shell structure with an I-beam with a cutout. And then towards the back again, definitely sheet metal. So mixed meshing is something that Reza talked about. And in this case, that would be the best way to approach this. But in the middle ground, these black pieces, there's no good answer, because you might need to make a level of idealization and then prove to yourself through physical testing or mini studies that your shell simplified idealized version of the black piece is actually accurate. So when you really need to start using shells is when you get into assemblies. And on the top right, you can see a cabinet, the top of the platform, and then the top of the whole tower that we're going to look at today. And there's absolutely no way you could solve that without being very proficient with shells. The problem is, why not just use beams? Well, the thing about beams is, to me, sometimes they're too simplified. Let me take you through a little side example to show you what I mean here. So let's say we're looking at the factor of safety on this industrial equipment frame. On the left-hand side, I've done my frame analysis using beam elements, but on the right, you can see the difference of shell. And right away, what you should see is the displacement is going to be pretty much the same. But when I'm really after granular results or stress results at the junctions, that's when I really want to get into shell results. So beam is fantastic because in 30 seconds I can make a design decision about, what wall thickness weldment do I need. In this case, go from 5/16 to 3/16, cut the price in half. Awesome. But when I start to get more towards validation and maybe looking at potential vibration analysis at the end of my design cycle, well, then I really want to have shells because it gives me that extra level of detail. For example, the brackets in the back, how do they really fasten with the bolts to the next part of the frame, and really being able to visualize what the response looks like. So one of the things we had to do in this analysis was do a time response. And you can do this with beams, but again, here I get a real clear picture of both the load path as well as the bending stress on the top and bottom of that weldment piece. Almost more importantly is I can pull out dynamic stress, so I can see right where the hot spot is going to be on the corner of this weld. And again, with beams, you're kind of oversimplifying it in a case like this where it's just going to be a single point, and you'd be looking at the forces to do a hand calc. So here I can really narrow in and add fidelity to my high stress areas and look at them over time. Or I also, in this analysis, had to look at, well, what's the reaction force on the fastener holes? Again, I can't have a hole in a beam element. So again, shell is my go-to whenever I have a structure like this or larger. Think about this, a garbage truck. The larger your analysis, the more you must be proficient and expert with shell meshing. And to do that, you got to be good with surfaces. So you could, again, model this thing with solid, sure, but if you just tried to mesh and run this as a solid, even the best engineering workstation, it would probably mesh fail. And even if you got a mesh to go on this thing, you never have two elements across the thickness. So a shell version of this, it might take an hour, 2 hours to start setting up the body, but then it's going to be solving in minutes. So it's definitely worth it. And again, something like this looks daunting at first. And I know a lot of first-time simulation users, they really want to get into it, and they open up their largest top-level assembly, and they want to apply, the grain loading, the pressure loading, and the weight, maybe a wind loading, and they want to go to town and get their answers, which is great. We just got to take a step back and realize that there's some prep work we have to do. Especially when you look at today's example, and again, this is a grain elevator tower, and I'm not going to analyze the whole thing, but I'm going to do the entire top platform, which is going to give you a really good idea of what the process looks like and how we can approach it. And that's really the goal for today, is find out the stress, factor of safety, displacement, let's say under a 10,000 pound loading on this platform. So let's talk about surface bodies inside SOLIDWORKS. Reza, in his episode on Sim Step Up, he talked about mixed meshing, and he talked about some of the same stuff I did in the intro. Bulky parts are solids, thinner parts can be shells, slender parts are beams. And he mentioned something very important, is that to make a shell, you need to extract the mid-surface or use sheet metal modeling. And I really want to dig into this in the next 10 minutes or so, because we really need to understand this. So there's 4 ways that you can make a shell element, or I should say specify simulation should use a shell element. If you're using SOLIDWORKS sheet metal, the sheet metal command, and you have a sheet metal feature tree, the mid-surface is automatically extracted and the body is defined as a shell in simulation. So that's done for you. Now you can also select solid faces, like the inside or the outside of your structure inside the simulation feature tree, and that converts it to a shell type. As you'll see, I don't really use this. It's my least favorite type because it's hard to keep track of to me, especially when you get into larger models. and it's a heck of a lot of clicking. And as we'll see, there's some more automated ways to specify the shell types. Now, we're going to focus a lot in the next few minutes on converting our solid models to surface. Number 3 there. This is, to me, the way to do it. But if you're more taking the design from concept all the way through validation, if you can build surface models initially with either design or validation simulation in mind, I'll show you a few examples where that is superior, because you're just going to start with a surface that goes right into simulation. So let's get started about creating surface and shells from solids. And I've broken it into 5 strategies. And the more you use SOLIDWORKS management or automation, meaning creating a shell from either a configuration or using automated sheet metal, the more the whole thing is going to be associative and stay up to date. Which is great, but it's more work to set that up, of course. So the more I'm working on a validation at the end of a design cycle, or maybe a one-off contract job for FEA, the less I care about maintaining associativity, and I'm going to thrash my assembly, even collapsing it into a single part. And one thing right now, if you haven't seen it, check out Mike Sandy, episode 101 on the Sim Step Up series, because he talks a lot with this same example about how to collapse down quickly a large assembly into a simulation-ready multi-body part. And I'm going to show you that as well today. But I'm going to start with probably the middle ground between complexity to set up, but then also benefit of having the shell mesh derived from your solid mesh. And that's creating a configuration in the SOLIDWORKS model. Okay, so we're going to be creating some surface features and then deleting the solid bodies and then configuring that so I still have my design configuration, but then also the FEA, which exposes the surface bodies, deletes the solids. So we're going to get into it. I'll show you. A couple key commands I'm going to use are definitely offset surface and mid surface and delete body. And the last 3 we'll talk about as we go through the rest of the examples. Let's get into the software and let's just isolate this platform up top. I can use my breadcrumbs D key to find the level I'm going to analyze. And let's do this second to the top level assembly. This is still a 3-level deep, so I'm going to open up until I find the base part level and basically scrub through every single part top to bottom in the tree and make surfaces. So we're going to add a new configuration and be consistent. I'm going to call this FEA shell, and I'm going to make that standard for my entire team. Now, the first command we want to try is just an offset surface. So I'm going to select tangency, get the entire beam, and notice the yellow preview, flip it, and this is the mid surface. It's a surface body at the middle point of the thickness. Perfect. Now I have a surface body, right? And I'm going to take that solid, and I'm going to delete body. I'm not just going to hit delete key, but delete body, and then I'm left with a surface and a solid. And the basic premise is I can configure this feature to suppress it in the design configuration, but open it up in the FEA. So now look, I switch between design and FEA shell, and I have that. Let's automate this though. Mid-surface command. You might have to use the S key to search for it. I'm going to find face pairs that are under 1/2 inch. And you want to set this threshold to be about your maximum material thickness plus a little bit. And this, as you can see, automatically went through and created the exact same surface body for me on everything. Now, one thing is you have a lot of surface, mid-surface bodies now, so I'm taking a measurement of my beams, and I'm going to rename my surface bodies to their thickness, just so I can keep that straight. So I have about 3 different thicknesses, so each one of those I'm just going to make a note of here and rename the body, so when I get to simulation, I can reference it very, very quickly. Let's fast forward a little bit here, and now that I have those 3 set up, I'm going to do a delete keep body and keep just the surface bodies. This gets rid of the solid bodies. And what I'm going to do again, of course, is configure that at the bottom. Okay? So configure that feature. And now I have default and an FEA shell configuration. Pretty awesome, right? Now I'm going to save that, go back up. At the higher level assembly, create the same configuration, FEA shell. In this configuration, I'm going to reference the FEA shell configuration. One thing I'm going to do is fix this, because as I start to bring in the shells, I'm going to break all my mates. So I'm going to fix in this configuration. So mid-surface is very powerful, very automated. You can also use the mid-surface command to simply select 2 faces, and in this case, create the mid-surface. Again, I'm going to do best practice with design and configure that surface and body delete and reference that configuration. So it's easy to keep track of this because as I change configurations, you can see in my feature tree, I have it, and then mass properties should give me this message that there's no eligible documents. So shells have no mass, or surfaces have no mass. So let's go up a level, make an FEA shell configuration, fix these components in this configuration because I'm going to blow up the mates, switch that subassembly to the FEA shell, and then get to work on the top one. Again, this is a lot of parts, and the only way to do this is go top to bottom, open them up. Now, this is actually a sheet metal part, and I'm going to come back to this real quick. But actually, if you have a sheet metal part, when I make a simulation, notice when I mesh it, it creates a shell mesh, infinitely thin shell mesh. So the only problem here is I can't change the thickness. I have to actually go back to the sheet metal fixture or definite feature in CAD and define that. So let me fast forward. All I'm doing is I'm opening the parts, making a mid-surface on all these plates and these structural steel elements, and then creating a configuration on those. Here's that top railing, a lot of bodies. And then I'm going to close it, save it, go up a level, and reference that configuration. So by the time I'm done, my entire feature tree at every level of my assembly should be referencing an FEA shell configuration. What's nice is if you're consistent with this naming scheme, it makes it a ton easier to validate it, as well as there's ways to automate opening an assembly and opening them all the reference components to a named configuration. All in all, this probably took me 30 or 40 minutes to set this up. So again, it takes a little bit of time and there's a faster way, but the benefit being now I have associativity back to my design, assuming everyone can keep it straight. And that's really the downside of this methodology. When I'm working by myself on the design and everything, it's great because I know my feature tree. But again, we're creating a big load of features at the end, so if people go in and add stuff after that or mismanage the configurations, it can get messy quick. So if you're going to do this, it works better with a small team where you all get it, have them all watch this. But the bigger the team, you're only as strong as your weakest link when it comes to managing configurations. So it's up to you. So sometimes keeping it in context is hard. Let me return to this idea of using simulation itself to define the faces and go back to that sheet metal example. So notice the sheet metal on the left-hand side. I have the sheet metal feature with a few applied features after that. And again, SOLIDWORKS is smart enough to take any sheet metal part and automatically mid-surface it. But I want to stress that while this is automated, it's great if I have smaller assemblies or if I'm not going to change the thicknesses at all. What you'll see in my study is I need to actually iterate on a few of the thicknesses. And so keeping this linked to CAD and using the automated sheet metal to shell is good, except that I'm going to have to go back to CAD to do any kind of iterations. So imagine if I had, 8, 10, 20 of these beams all around and I want to try them all with 1/4 inch or 3/8 or 3/16 thickness. I have to go back to the CAD model for each and every one to iterate on it. So you can also specify a shell model simply by clicking a face in the simulation. So you actually mesh it on the surface and then it offsets it. And there's this idea of top and bottom and middle surface. And when you click a face in simulation, you can actually tell the software, hey, does this face represent the outside, the inside, the mid surface, or a different offset? So it's really awesome. It speeds it up because you don't have to create all these surface bodies. But again, if you're at any level of complexity in your assembly or you want to do any kind of iteration, I really like to just create the surface bodies and get rid of the solids and really validate that I have it all set up correctly. One reason is because if I have a big solid model and I go into simulation, and try and set everything up by clicking on the solid faces, a lot of times I'll forget one of the solids and all of a sudden I have a solid model floating around in there somewhere. So I like to give simulation the whole chunk of shells that I'm going to use and make sure it's just chewing on that. So as you get more towards a validation, you can do a pack and go, right? Create my own copy of the assembly with maybe a -FEA suffix on there. If you haven't seen Mike Sandy's episode number 101 on SOLIDWORKS for simulation, I want you to watch that now. In fact, we're going to pause for today. We did a lot of work creating those configurations. There is a much, much faster way if you're ready to kind of thrash a little bit. But I want you to watch Mike Sandy's episode and then come back for part 2 of this episode Well, we'll do it the easy way and then get into meshing, contacts, and looking at the results and validating that everything looks good, both on the contact and the result side. Thanks for watching part 1, and let's get to part 2 next time.